Steep Carbon Trends presents Hydrogen for a Sustainable Future. Why do we need hydrogen? Hydrogen, with the chemical formula H2, is a gas with many advantages. It is non-toxic, has a high energy density, and is a component in almost every organic compound on Earth. Moreover, hydrogen is applicable in diverse sectors, ranging from chemical production, metallurgy, energy to mobility. Hence, it could replace fossil raw materials for multiple purposes and play a key role in decarbonizing major sectors of our economy. However, hydrogen is not just hydrogen. There are numerous ways to produce hydrogen. Its sustainability largely depends on how it is produced. How can we produce hydrogen? Hydrogen can be produced in different ways using diverse input materials. Each production route has been assigned a different color to indicate different degrees of sustainability. Today we speak of gray, blue, turquoise and green hydrogen. Gray hydrogen is produced from natural gas in steam reformers. This is a well-established process which has been in use for decades. However, the combustion of natural gas in the steam reforming process at temperatures above 800 degrees Celsius results in the production of large amounts of CO2 emissions. To improve the carbon footprint, the CO2 emissions can be captured and stored, for example in mines or old natural gas reservoirs. This process is called carbon capture and storage, in short CCS. If this is the case, we speak of blue hydrogen. For turquoise hydrogen, natural gas is converted to hydrogen via a different process called methane pyrolysis. During this process, natural gas is heated to temperatures above 800 degrees Celsius in the absence of steam, which breaks it down into its elements hydrogen and carbon. The carbon occurs in the solid form and can either be stored in mines or be used for production, such as for car tires. This is a key advantage of the methane pyrolysis process, compared to the steam reforming process, where carbon is produced in gaseous form as CO2. However, both processes use natural gas, a fossil resource, as input material. In order to produce hydrogen sustainably, alternative input materials from renewable sources for the production of green hydrogen are required. How can we produce green hydrogen? Green hydrogen can be produced via different routes. One route is via electrolysis, where water is split into oxygen and hydrogen. The source of electricity used to power the electrolysis determines whether the hydrogen produced is green. Green hydrogen is produced when renewable energy sources such as wind, solar, hydro or geothermal power plants are used to generate the electricity required for the electrolysis process. Other routes use biogenic materials as input. As biogenic materials are renewable resources, carbon emissions during the production process are considered to be CO2 neutral. Hence, in replacing natural gas with biogas as input, green hydrogen can be produced via biogas reforming or biogas pyrolysis. In addition to biogas reforming and biogas pyrolysis, bio-waste gasification is another route which uses biogenic materials as input for producing green hydrogen. Specifically, biogenic waste such as waste wood and forest residues can be converted to syngas via gasification process under high temperature and high pressure conditions. Syngas is a mixture of carbon monoxide and hydrogen. These two components can then be easily separated from each other. How sustainable are gray, blue, turquoise and green hydrogen? To assess the sustainability of different routes of hydrogen production, the carbon footprint is an important indicator. However, it is not the only determinant for sustainability. Other criteria to consider range from fossil resource demand, energy demand, availability of input materials to production costs. Let's consider gray, blue and turquoise hydrogen. All three production routes have a high demand for fossil resources in the form of natural gas as input material. This demand is met by the global availability of natural gas, and thus presents no limitation to their production. Although grey hydrogen has a high carbon footprint, the low energy demand as well as low production costs have led to its dominance in terms of hydrogen production worldwide. Today, over 90% of the world's hydrogen consumption is produced this way. In contrast, blue hydrogen has a low carbon footprint, as CO2 produced during the steam reforming process is captured and stored. However, the lowering of the carbon footprint is associated with a higher energy demand as well as higher production costs compared to grey hydrogen. Turquoise hydrogen is similar to blue hydrogen along diverse indicators. It has a low carbon footprint as solid carbon produced during the methane pyrolysis process is captured and stored. This also translates into a higher energy demand as well as higher production costs compared to grey hydrogen. Note, however, that pyrolysis technology is more complex than reforming and is still in the development stage. Now let's consider green hydrogen. The use of renewable and biogenic materials as input means that no fossil resources are required for all green hydrogen production routes. However, their performance along different sustainability criteria differ, according to how green hydrogen is being produced. Green hydrogen produced via water electrolysis, powered by renewable electricity, has zero carbon footprint. However, the energy demand leads to high production costs. Moreover, it also depends on the availability of renewable energy. Green hydrogen produced via biogas reforming without CCS would have zero carbon footprint. With CCS, negative carbon footprint can be achieved. As this utilizes an established technology similar to conventional steam reforming, its energy demand is similar to grey hydrogen, though production cost will be higher. A key limitation for this production route is the low availability of biogas. Green hydrogen produced via biogas pyrolysis will also have a negative carbon footprint. Its energy demand is higher than biogas reforming but lower than water electrolysis. Besides similar production cost as biogas reforming, it is also limited by the low availability of biogas. Moreover, the technology is more complex than the biogas reforming process and is still in the development stage. Similar to biogas reforming, green hydrogen produced via bio-waste gasification without CCS will have zero carbon footprint and negative footprint with CCS. While it also exhibits similar energy demand as biogas reforming, production cost is higher, as higher investment for the gasification plant equipment is required. Its advantage, however, is that biogenic waste as input is readily available. As you can see, hydrogen is not just hydrogen. Which hydrogen production route is most sustainable is not an easy question to answer, as it is not just a matter of carbon footprint. Hydrogen in different forms, be it grey, blue, turquoise or green, could play complementary roles in decarbonizing major sectors of our economy. A systemic overview of their strengths and weaknesses along multiple sustainability criteria can support us in developing a hydrogen economy for a sustainable future. A short animated film by the junior research group Global Change Steep Carbon Trends at the Institute of Energy Process Engineering and Chemical Engineering, TU Bergakademie Freiberg.